let's talk now about the so-called principle of the argument theorem. So according to this, if we have some complex function f, and if we are interested in some contour c, so for instance, if we imagine our S-plane, so the S-plane, of course, has an imaginary axis and a real axis here, and then there's some contour c, then the principle of the argument says that if we consider a certain function f, which has z zeros and p poles inside of that contour. So remember, we said a pole was a value of s where the function went off to infinity. And by the same token, we can define zeros. So those would be s values where the function goes to 0. And if you look at this, you can see here when s equals z1, then the function goes to 0. When s equals, the function goes to 0. Yeah. And then when s equals z2, then also the function goes to 0. And when s equals p1, then the denominator is 0 and the function goes to infinity. So we can see here 2 zeros and 1 pole. And we've drawn a contour, and we can see here that we have the 2 zeros shown, and we have 1 pole shown. And according to principle of the argument, if you have this contour C, and if you travel around a closed circuit of C, so in other words, if you consider different S values, so let's say we started here, and this was the S value of the real part being, let's say, 3, and the imaginary part being maybe 1.5. And then as we traveled around here, and we've got different real parts and imaginary parts, so as we travel around this contour, going through all those S values, then our function f, right, and this function f, that would be going through its own set of values. So once more, this is the S-plane. This is the independent variable plane. And we can imagine that our function f, and that might be something we'll be drawing in a different plane altogether, then that function f will be going through its own set of values as well. And according to the principle of the argument, that if we have z zeros and p poles, then the number of times that function f will encircle the origin will be z minus p times. So once more, we are traveling around S here, or around C, this contour. We are taking on S values along this contour. And of course, we could have chosen any S values. We could choose a line here or a line there or a different contour there. But we have chosen specifically this contour. So we are looking at all the S values as we travel around this, as we go through all the S values along this contour. Then if there are these 2 zeros and this 1 pole here, then as we travel around these S values, our f function is going through its own real and imaginary numbers, and f will actually encircle the origin 2 minus 1 times. So that's what the principle of the argument says, that we will encircle, f will encircle the origin z minus p times, where, of course, z is the number of zeros and p is the number of poles. So that's what f will do. It will encircle the origin a certain number of times as we choose s values encircling this or traveling along this contour. So this is a result that's going to matter quite a lot in terms of our control strategy. So we can illustrate this. So we aren't going to do a rigorous proof, but we'll just illustrate why this is in fact obvious. And we'll do that just by example here. So we've introduced already this example for f. We haven't specified actual numbers for z1, z2, and p1, but we're saying there is some contour like this, and those values are in there. So now let's consider walking around this contour. So let's say we start with an S value here, and let's consider S minus Z1, right? You can see we've got that in our numerator, S minus Z1. Well, S minus Z1, you can see will have a real part which has a magnitude up to there, and the imaginary part is 0, right? If we've chosen a point on here, which is directly alongside the circle. So if it has the same imaginary value, then the imaginary value here minus the imaginary value there, right? That's what we get when we take S minus Z1. So the imaginary parts, if there's no difference, then that's going to be 0. And then as we travel around, imagine we get up here, directly above this point. Then we can see the imaginary parts are not the same. They won't be 0. The real parts, the difference in the real parts will be the same. And so the angle in this case is 90 degrees. So if you take a point here, you can see that's the line we're looking at. And then if we measure the angle from this line, so between these two lines, we can imagine a 90 degree. So we started out from an angle of 0. We've traveled around to a plus 90. And if we keep going, then we get a plus 180 degrees. Keep going, we get to a plus 270 degrees. Then we get to a plus 360 degrees. So as we travel around this, we get a plus 360 degrees. And then if you do the same thing from the perspective of the other 0, so as we've traveled around, and we had started here, so we had some angle there. As we travel around, we can see, and we stop at the same point. So it's a closed walk. So as we do that, we get a plus 360 degrees there as well. So each S minus Z value goes through a plus 360 degrees. And similarly for S minus P1, if we consider from the perspective of the pole here, so we've chosen here, and we can see the angle is going to increase by a plus 360 degrees. So S minus each of these values, if we look at the walk around that value, it's going to be a plus 360 degrees. And then if we think about the argument of F, right? And of course, the angle of F is obtained as the angle of each of the pieces. And we know that if we represent this in polar coordinates and multiply it all together, then it's simply the sum of all the angles. So the sum of the angles in the numerator minus the sum of the angles in the denominator. Then we can see we will increase by 360 degrees for each 0, and we will decrease by 360 degrees for each pole. So that's why we say that the angle of F, right, the number of times F will go around the origin will equal the number of zeros minus the number of poles. So in fact, it's quite obvious when you look at this simple example that yes, our function F is constructed in this way. Each of these factors go through 360 degrees, and depending on where they are sitting in the function F, they will either increase or decrease by 360 degrees. And if you think about a point on the outside here, let's say we had a point sitting here. As you go around this contour, the angle for this point is not going to go through 360 degrees. So if we draw, for instance, a dot here, and if we consider the angle in each case, you can see the angle will go up, it will come back to the same position. So the moment we are outside, let's say the Z1 was moved outside of the contour, then the angle will increase and decrease and come back to the same value. So when we are outside of the contour, the angle will not increase by 360 degrees. So it's only when we are inside of the circle that we'll observe F going through that number of encirclements. And that's going to be a tremendously useful observation for developing our control methods.